Hi, welcome to Elasticity. Today we are going to continue our lesson on how to measure distortion. This time we are going to actually measure how things change and how to measure changes in lengths and angles. So just a quick recall, remember that when we started this, we looked at a small line segment. So that's y-axis, that's x-axis, and we looked at a small line segment like that, PQ, and it became a line segment, a short line segment like that, little p little q. Okay, and we had the vector PQ was delta x in the I direction, delta x1 plus delta x2 in the j direction. So I'm not going to write delta x and delta y because I want to use index notation, and so I'm going to switch to delta x1 and delta x2. For future, I am going to calculate the length of this. Capital L is just square root of delta x1i plus delta x2j. Sorry, square root of delta x1 square plus delta x2 square. Well, that's no biggie, right? It's just length. Fine. And then the unit vector along PQ equals delta x1 over Li plus delta x2 over Lj. This will be called the T vector, and this has components delta x1 over L, delta x2 over L. So far nothing major, we are just recapping what we did. Then we computed little p little q, and we found out that it was approximately equal to, the approximation gets better as delta x1 and delta x2 get smaller. So little pq equals a F matrix times delta x1 delta x2, and this F matrix looks like I plus gradient of u. In index notation, this looks like Fij delta xj, right? And Fij equal to delta ij, that's that, plus ui comma j. Usually, if you really ask me why, I have to get into a long discussion, but typically the second index is written in terms of capital letters for various historical reasons and so on. So in a typical textbook you will find this. There is no difference, and this will be written as PQ, the ith component of PQ will be FIA delta XA. It's common notation, don't ask why they put this, that and the other, but that's what we have. Very good. So now we want to come and calculate engineering strain. Engineering strain equals change in length divided by original length, right? Which is little l, which is the length of this thing, divided by capital L minus capital L. Can you see that? Which is little l over capital L minus 1. So we already know what is capital L. It's out here. We just have to calculate little l. And it turns out it's easier to calculate little l squared, because that is the magnitude of the vector PQ squared, which is PQ dotted with PQ, which is PQ. Now that we know index notation, it's PQI, PQI, right? That's easy. I know I have PQI here. And remember, I am not going to repeat the A index again. You remember our rule in class recently. So this is FIA delta XA. That's that one. And this one will be FIB delta XB, which is FIA FIB delta XA delta XB. Now you can see the advantage of index notation, right? This is some matrix and it's called the CAB matrix. And this, my friends, is probably the most important matrix in the measurement of deformations, the CAB, and it is called the Cauchy-Green stretch matrix. Well, what it is that in matrix version, this looks very nice. Remember, this is, notice, it is column times column, right? It is not row times column. You see what I mean? So column times column represents A transpose A. So C matrix equals F transpose F matrix, which is I plus gradient of U transpose times I plus gradient of U. I am doing this in matrix notation, which turns out to be I plus gradient of U transpose plus gradient of U plus gradient of U transpose gradient of U. This is in a direct notation. Let us see it in index notation. CAB equals FIA FIB. What is FIA? It is delta IA plus UI comma A times delta IB plus UI comma B. Expand it out, you will get delta IA plus UI comma A plus UA comma I plus UI comma B UI comma A UI comma B. So delta IA is this guy, UI comma A is here, is here. Hey, apologies, I did the same mistake twice now. So UI comma A is here, UA comma I is here, UI comma A, UI comma B is that. So it looks like, and this is so important that we are going to write down every term. So C11 equals 1 plus U1 comma 1 plus U1 comma 1 plus 2 plus UI comma 1 UI comma 1. You can expand that, U1 comma 1 U1 comma 1 plus U2 comma 1 U2 comma 1 and so on. C12 equals 0 plus U1 comma 2 plus U2 comma 1 plus UI comma 1 UI comma 2. C22 is 1 plus 2 times U2 comma 2 plus UI comma 1 UI comma 2. Sorry, UI comma 2 UI comma 2. And if you had more components, you can write it. I will leave some space. You can figure out if there are 3 components, what will be C33, what will be C23. This C matrix contains all the information that you need about how things deform. So this is the most important matrix. Okay, but we kind of seem to have gone off on a side track, no? So let us go back to our main track, which was L squared. Looks like this, right? So let's go back. Let's kind of regroup now, and I will write L squared. L squared was CAB delta XA delta XB, which looks like C11 delta X1 squared plus C12 delta X1 delta X2 plus, you can fill it out, right? But what I am interested in is epsilon equals L over capital L minus 1, which is equal to square root of CAB delta XA delta xb divided by L minus 1. Okay, which I can write it as square root of CAB delta XA over L delta XB over L minus 1. So why did I do that? Because I can go up here and you will see that the components of T have delta x1 over L, delta x2 over L, and T is the unit vector. So I don't even need to actually know delta x's here. To compute the strain, the engineering strain, square root of CAB TA TB minus 1. So this is F transpose F. This components of unit vector along the direction in which you are computing strain. You can see it's some nasty square root and then it's CAB, TA, TB, and there's a whole bunch of terms here, right? There will be 4 terms if you are doing in 2 dimensions, 6 terms if you are doing in 3D. That's how it works. So we now have computed the strain, change in length over original length. Now let us go back and let us look at other things, which is changes in angle. For this, it is not enough to look at just one line. I have to look at 2 lines. So remember, I had this. Let us call this PQ, and this point is R. This angle is right angle. This length is delta X, that length is delta Y. Okay. What happens after deformation? It becomes like this, right? So this is little p, this is little q, this is little r. So let us call this length L1, let us call this length L2, this is capital L1, capital L2. So capital P, capital Q equals delta xi. So T1 equals 1 0. Unit vector in this direction is 1 0. The unit vector in this direction, which is called T2, PR equal to delta yj, T2 equal to 0 1. Hey, that's pretty nice. So now let us look at PQ. PQ equal to F times the vector F times capital P, capital Q, that is delta X 0. PR equal to F times 0 delta Y. So we know how to compute the strain epsilon PQ, which is also called epsilon X, strain in the X direction. That's easy. That's equal to CAB T1A T1B, right? T11 equal to 1, T12 equal to 0, T21 equal to 0, T22 equal to 1. What the heck? Plug it in, and this you will get very simple. Sorry, square root minus 1. So square root of C11 minus 1. Everything else will be 0, because if you write down this, it is C11 T11 squared plus C12 T11 T12 plus blah blah blah. This is 0. All the other terms will be 0. So you'll be left with only this, and T11 is 1. Hey, that is very nice, no? Epsilon PR equal to epsilon y. By exactly the same reasoning, this will be square root of CAB T2A T2B minus 1. If you compute this, this is square root of C22 minus 1. Okay, so we computed this one is square root of C11 times capital L1 delta x. This one is square root of C22 delta x. What we are interested in is this angle. So I'm going to redraw that so that we can see properly. This angle is called gamma, this angle is called theta, and the shear strain is tan gamma, tangent of this angle. You're wondering why tangent? So what do you want for the shear strain? If it looks like this, if it looks like this, we want gamma equal to 0 implies shear strain 0. If it completely folds over, gamma equal to 90. What do you want? You have squished it completely. Of course, this is impossible, no? So you want shear strain to be infinity here. Okay, so you can get shear strain 0, you can get shear strain infinity. So the function that works for this is tan gamma. Tan gamma has beautiful features, and one of its key things is when gamma equal to 90 degrees it's infinity, when gamma equal to minus 90 degrees it's minus infinity. So it's very nice. So if when the thing goes like that, gamma, this corresponds to shear strain tan gamma equal to minus infinity. This corresponds to tan gamma equal to plus infinity. So everything is nice. This is tan gamma equal to 0. So shear strain is the tan of this angle. Turns out to be a pain to compute. So let's try if we can do something about this. We know this length. This is square root of C11 delta x. We know this length, square root of C22 delta x. This is little p, this is little q, this is little r. What I want to do is find gamma and then calculate tan gamma. But the easier thing to do is compute cos theta or sin gamma. Sin gamma is easier to compute. How am I going to find sin gamma? That's pretty easy. Sin gamma equal to cos theta, right? Cos theta is PQ dotted with PR divided by L1 L2. Why do I think that? Because A dotted with B is magnitude of A, magnitude of B, cos theta. So cos theta is that. How do I compute PQ dotted with PR? Go back to my original matrix. It's here. PQ is here. PR is here. F times delta x 0, PR is F times 0 delta y. If you compute that, PQ dotted with PR PQ dotted with PR equals F times delta x 0 dotted with F times 0 delta y. Which is equal to delta x comma 0 F transpose F 0 delta y. Hey, this is our familiar C matrix. I told you, C has all the information. So remember that, okay? The C matrix is F transpose F, has everything you need. You just have to extract it from it. It's a little bit difficult. Okay, so PQ dotted with PR is that. If you expand this, this will turn out to be very nice. This will just be C12 because there's only first term here and second term there. Those are the only non-zero things. C12 delta x delta y. Right? So now we get sine gamma equal to cos theta equals C12 delta x delta y divided by square root of C11 delta x, that's L1, square root of C22 delta x delta y, that's L2. So the delta x delta y will get cancelled. So it is C12 divided by square root of C11 square root of C22, which is C12 divided by square root of C11 C22. Now you can compute tan gamma equals sine gamma over cos gamma, which is sine gamma over square root of 1 minus sine squared gamma, and sine gamma is this. So you can substitute it there and do some very painful simplifications, and you will get a kind of a messy thing which turns out to be C12 over square root of C11 C22 divided by 1 minus C12 squared over C11 C22, which is C12 divided by square root of C11 C22 minus C12 squared. That's the shear strain. So to remember this picture, I'm going to draw something that's pretty nice, and then you will see how this thing works. So this is PQR. This picture is very important, so please memorize this in your head. I'm going to call this 1 unit, 1 unit. It's not really, it's supposed to be short, but I'm calling it 1 unit. My final deformation looks like this. If this is 1 unit, this is square root of C11. This is square root of C22. This angle and this side is C12 over square root of C11. So if you remember these three things, square root of C11, square root of C22, C12 over square root of C11, you can find the angle. Sine angle is this and this, cos you can find out what is this length and so on, and it's pretty easy for you to figure out everything. So this is the picture to remember. Okay, we have one last thing to do. What happens when gradient of u is very small? So specifically we are going to say magnitude of gradient of u is very small. So what do we mean by that? Look, when I'm going to deform something, right, I'm going to talk about a nearly rigid body. it's a nearly rigid structure. It's not going to rotate. It's going to deform very slightly. So what happens when gradient of u becomes very small? Remember, CAB was delta AB plus ui comma a plus, where did I have that? Sorry. Let's write this down properly and then I will do that. Okay, sorry about that. I just wanted to make sure that my notation was correct. Okay, so C equal to F transpose F, which is equal to I plus gradient of U plus gradient of U transpose plus gradient of U transpose gradient of U. Right? So CAB will be delta AB plus UA comma B plus UB comma A plus UI comma A UI comma B. Okay, we are expecting this to be small. This to be small. Then this will be very small. So we are going to quietly throw it away. So then my C matrix looks like I plus gradient of U plus gradient of U transpose plus terms of order epsilon squared, which we have thrown away. So this is approximately equal to. Excellent. Things have progressed. Now see, I don't have any quadratic terms, I only linear terms in C. Not only that, what about my epsilon x, which was square root of C11 minus 1, right? Which is square root of 1 plus, because C11, if you put A equal to 1, B equal to 1, I'll get 1 plus U1 comma 1 plus U1 comma 1. So 1 plus 2 U1 1 minus 1 approximately, which turns out to be approximately equal to 1 plus 2 U1 comma 1 to the power half minus 1, which will turn out to be U1 comma 1. Hey, that's very nice. Look at how simple it is. It's just gradient of U, the first term. Epsilon y will turn out to be approximately equal to U1 comma 2. Sorry, U2 comma 2. Very, very nice. How about gamma? So which is, sorry, tan of the angle gamma, which is called kappa, which is the amount of shear, is approximately equal to gamma, which is approximately the same as sine gamma. Hey, this is really cheating. But if you write Taylor series, you will see that both tan gamma and sine gamma start with gamma. So we are going to keep only that. So which is approximately equal to C11, sorry, C12 over square root of C11 root of C22. This will be approximately 1. That will be approximately 1. So this will be approximately U1 comma 2 plus U2 comma 1 plus other terms. So we have a very nice result. Epsilon x is U1 comma 1. Epsilon y is U2 comma 1. Sorry, U2 comma 2. Gamma kappa xy. And in many textbooks they will call it gamma xy because they are using tan gamma is gamma. So many textbooks will write this as just as gamma xy is U1 comma 2 plus U2 comma 1. All of them neglecting quadratic terms. With that, we are done. This is important. This picture is important for you to find everything. That picture is important, and just here I'm going to write F C equals F transpose F, which is I plus gradient of U plus gradient of U transpose plus gradient of U transpose gradient of U. This picture is important. With that, we are done. Thank you.